When NASA unveiled the secret results of their most recent propulsion test, the scientific community waited for a ripple effect. Instead, they received a tsunami. Decades of pursuing the dream of traveling faster than light speed ended with a veil lifted to showcase what most had speculated behind closed corridors and theoretical physics communities. NASA had perfected a propulsion system so advanced, so radically transformative, that it was capable of accelerating to light speed. Not relativistic speed, not near light speed, true light speed, 186,282 miles per second. What the implications of this confession are is mind-boggling, weaving together the bold fantasies of science fiction and the ever more daring path of new physics. The key to this achievement is a propulsion system that defies traditional rocket dynamics. The engineers at NASA, along with a crème de la crème group of quantum physicists and materials scientists, constructed a working prototype engine based on principles that had previously been theoretical or outright impossible. They've seemingly tapped the enigmatic properties of zero-point energy and quantum vacuum fluctuations, phenomena that draw from the hidden energy of empty space. This source of energy, previously intangible and impossible to measure in real-world terms, has been domesticated using quantum field manipulations and sophisticated containment protocols with the aid of metamaterials that do not occur naturally. The outcome is a drive system that taps into the intrinsic energy of the vacuum itself, needing no fuel by conventional standards. The engine, informally referred to as the light drive among the participating engineers, operates not according to Newtonian principles. It doesn't shove mass aside to go somewhere. Rather, it reshapes spacetime itself on an infinitesimally small but precisely controlled scale. Resembling the Alcubierre metric, a formerly purely conceptual framework which described warping spacetime to enable traveling faster than light, this technology warps the space ahead of and behind the vehicle, squeezing space in front while stretching it in back. The vehicle technically doesn't budge inside a warp bubble, space itself moving instead. Light is still the local cosmic speed limit, but this push defies that boundary by changing the fabric of spacetime itself. The experiments on which this breakthrough was based were kept under wraps for decades, hidden in the files of NASA's Deep Space Propulsion Program under code names. Concealed in secret budgets, masquerading as advanced materials testing and vacuum field stability research, the work was invisible even to most of NASA's own personnel. A small team of scientists labored in buried underground facilities where all entrances were biometrically authorized, every conversation was monitored, and every outcome was classified above top secret. For participants, it seemed like life in science fiction books, with this difference that the equations on their whiteboards were genuine, and the vibrating prototypes in the vacuum chambers were no longer figments of imagination. But rumors seeped out. A few anonymous papers made their way onto fringe physics websites, speaking of stabilized quantum vacuum asymmetry. Cryptic messages crept into esoteric preprints. Conspiracy theorists wrote of warp engines and blacked-out test flights. The rumors became loud enough that NASA no longer could treat them as mere rumor-mongering. When the data reached a point where it could not be disputed, NASA took the unprecedented step of confirming the existence of the light drive. Although the admission was made with caution and plenty of disclaimers, none of it muted the shockwaves that ran through the scientific community. In a test chamber several miles from prying eyes, a small prototype vehicle roughly the size of a family car was fired inside a vacuum chamber that had been upgraded with magnetic field stabilizers. Engineers huddled around reinforced glass, their palms shaking as the countdown reached 0. Preliminary estimates were that it could achieve a meaningful percentage of light speed, maybe up to 70%. Rather, the vessel disappeared in an instant of brilliance, breaching the boundary of light speed itself. Gigahertz sensors operating at 1 billion frames per second verified what was once merely simulated. For a fleeting moment, the ship was in a relativistic frame. And then it was gone, leaving only disturbed airstreams and terabytes of data that will occupy scientists for years, if not decades. This achievement marks the end of the tyranny of distance for space exploration. Previously, Alpha Centauri, our closest stellar neighbor at 4.37 light-years away, was a bitter reminder of cosmic constraint. Using conventional propulsion, even the speediest probes would take tens of thousands of years to get there. Now, with light drive technology, it is possible within a human lifetime. A journey that once was the very stuff of interstellar fantasy might, in principle, be accomplished in a bit more than 4 years. For younger generations brought up on Star Trek and Star Wars, this is the moment when fantasy meets physics in the grandest possible manner. Technically, the feats overcome to accomplish this propulsion are simply monumental. The first challenge was that of energy. Zero-point energy was previously extracted and stabilized without triggering ruinous quantum instabilities. Past attempts created turbulent collapses of energy fields, unstable plasma outbursts, and devastating quantum fluctuations that could have destroyed the experiment chambers themselves. It was only when NASA scientists created a containment lattice constructed of programmable metamaterials that could dynamically adjust to quantum stress that the challenge was overcome. These materials, built at the atomic level, permit electromagnetic fields to warp and energy signatures to be manipulated in real time. With this technology, they were able to generate and maintain a quantum vacuum energy gradient, a requirement for initiating the spacetime compression that fuels the light drive. Navigation presented the other significant challenge. Classic spaceflight relies on reaction-based control surfaces and inertial guidance systems, both of which are made obsolete by light-speed travel. Navigation at those speeds demanded an overhaul of spacecraft orientation and destination tracking. NASA developed an AI-driven navigational matrix that could predict gravitational wells, spatial irregularities, and time dilation effects in real time. This AI is not only reactive, it proactively corrects trajectory according to predictive modeling based on quantum entanglement data and stellar location far into the spectrum beyond visible light. All new mathematical models had to be created in order to define predictive positioning, a means of laying out a ship's path not where stars are located, but where they will be years, or even decades, in the future, when the ship comes out of its journey. Of course, achieving light speed poses more than navigational and mechanical issues. Time itself is an issue. The theory of relativity described by Einstein stipulates that as the object gets close to the velocity of light, time will appear to slow down for it compared to an external observer. The light drive's special warping of spacetime cancels this out inside the warp bubble. Time still moves linearly within, although the bubble itself travels at light speed across the universe. That temporal isolation ensures that a crew aboard a light drive vessel would see travel to a distant star system occur in real time, without the paradoxical time differences anticipated by relativistic flight. It is a resolution of the twin paradox that has plagued relativistic spaceflight for over a century. The light drive is not only a technological advance, but a philosophical one. It makes human beings rethink their position in the universe. The stars are no longer distant points in the heavens, they are destinations. The galaxy of billions of possibly habitable planets is no longer distant but reachable. The existential implications are staggering. What does it mean to be human when the limits of our lives extend beyond our solar system? What does society become when an individual can ride to another star and home again before his family has aged more than a decade? Religions, philosophies, and cultures founded upon the peculiar nature of Earth and the vastness of the heavens will all come under new examination in light of the potential that humanity may tread on the soil of other suns within a single lifespan. NASA's admission also heralds the onset of a new era in geopolitics. Space has been a stage of competition for many decades, but light-speed travel shifts the very terms of that competition. The country or alliance that develops this technology earliest and best might control access to otherworldly resources, inhabitable worlds, and deep space scientific exploration. It ushers in a new kind of space race, a race not characterized by orbit or landing on the moon, but by interstellar extent. Think tanks are already pinning scenarios. What if the first light drive vessel arrives at a mineral-bearing exoplanet and claims it? What if another country does it years after? Will the treaties made on Earth be valid in the silence between stars, or will human history be replayed on galactic borders? There is also a psychological accounting to be made. Mankind has always gazed up at the stars as signs of the divine, the unattainable, the ultimate enigma. Light-speed travel dispels some of that enigma and substitutes it with opportunity and obligation. The exploration of space, once the subject of far-off dreams, is now a moral and cultural necessity. How do humans approach new worlds? What values inform our initial contact with other solar systems? Will we be explorers or colonizers, scientists or settlers? Will we approach new worlds as sacred lands to be respected or resources to be exploited as has been done with Earth? The NASA admission rewrites even our notion of physics. The light drive shows that long-held presuppositions regarding the impenetrable speed of light are perhaps not limitations, but barriers. The breakthrough confirms other readings of quantum field theory and lends support to maverick theories once dismissed by mainstream physics. Scientists who previously dreaded derision for suggesting spacetime manipulation now have their careers resuscitated. Conferences are swamped with new submissions, university departments are overhauling their curricula. The distinction between science and science fiction is narrower now than at any time in history. Theoretical advances in the future will probably be sparked by this achievement, creating new models of the universe and potentially even advances in the understanding of gravity, dark matter, and the unified theory of all things.